I'd like to do a quick demonstration of this device that was built back in 1915, just a couple of years after the Titanic sank. And what it is a Leeds and Northrup Type S Wheatstone Bridge testing device. And this was developed as a way of performing very precise measurements of resistance using a device called, or a principle called the Wheatstone Bridge, which was invented as a way of using known resistances as a means of determining an unknown resistance. I'm not going to talk a lot about the specifics about how that device actually works. You can look that up, and there's some very good YouTube videos about it. But I am going to demonstrate how this particular device can be used. And again, it's about 110 years old, and it actually gives a accuracy reading very comparable to modern digital multimeters, and I'd like to demonstrate that. So what I have here is a set of Radio Shack resistors, 5.6 kilo ohm resistors, or 5,600 ohms. And I'd like to demonstrate how this can be used to measure that resistance. So we're going to take one of the resistors out of that package, and I'm going to mount it onto the test terminals in the lower right portion of the device. And we'll tighten those down. And we're going to set the multiplier, which is this knob here, at 1. So the readings that we get, we multiply by a single ohm. So essentially we can read the dials directly to get the resistance readings. The 4 knobs here give 4 digits of precision on the measurement. This is the thousands digit, this is the hundreds, this is the tens, and this is the ones. The way this works is you take a trial reading on the thousands digit. Excuse me. You depress the 2 buttons here and read the meter, which you see deflecting all the way to the right. If this deflects to the right, that indicates you need to add additional resistance into the circuit. And the objective is to set all 4 of the dials such that when you press the 2 buttons down, you get no deflection at all on the meter. It reads 0. So we're going to, we can see here it reads well into the positive, so we need to add additional resistance. We know it's 5,600 ohms, so I'm going to start it at about 4,000 ohms, and it's still pegging. Now there, if I go to somewhere between 5 and 6, we can see that it's shifting signs. So we're going to leave it at 5, and then we'll start turning the hundreds digit. And I would expect somewhere around the 6, you'd expect to see it. There we can see it starting to move toward the center. The 500 is just about 0. If we go past it, we see we're in the negative region. So we're going to go to the point where we need to add resistance, and we're going to make that 5,500. Now, let's actually make it 54, see if we can adjust that down to 0 with the tens and the ones digit. So we'll slowly add resistance in tens of ohms. You can see we're getting down pretty close, and that is 5,900, and we're still just slightly to the right of the null position. We'll add single ohm. And I'm going to say the 9 is probably about the best. So reading this, it's the ohms reading is 5499, or 5.499. And the actual nominal value is 5,600. So we're going to compare that to a digital meter reading here. Again, we have 5499. So I'll move this out of the way. And we'll use this old fluke meter, which is not the most accurate device, but it's probably good enough for our purposes here. So I've got it set for resistance, and we're going to take the resistor out of the terminals on the bridge. And just holding the leads here, we see we are at 549. And we actually have an extra digit of precision off of the Leeds and Northrup device, the Wheatstone Bridge. So that agrees almost exactly, in fact exactly, with what the reading we got off of the Wheatstone Bridge, which was 5.499, and we have 5.49 here. So there we have a 110-year-old device, essentially providing better performance than we get from a fairly contemporary Fluke 77 multimeter.